Quantum telepathy has always sounded like the stuff of science fiction, but a major breakthrough has shattered that boundary and brought it squarely into reality. Researchers at the University of Colorado Boulder, in collaboration with Quantinuum, have demonstrated quantum pseudo-telepathy using an advanced laser-controlled quantum computer. This isn't just an impressive demonstration to wow the science community. It is a defining moment showing that error-resistant, scalable quantum computing is no longer a fantasy but an achievable reality. This is one of those rare milestones where the line between imagination and technology gets blurred, and in doing so opens doors to an entirely new future. At the heart of this astonishing achievement lies a simple but profound idea, a quantum game inspired by the theoretical work of physicist David Merman back in the 1990s. The rules are deceptively straightforward. Players are tasked with filling out a grid with zeros and ones based on specific mathematical questions. But there's a critical twist. During the game, the players are not allowed to communicate with each other at all. Under classical physics and traditional logic, no matter how clever or sophisticated the player's prearranged strategies are, there is no way to guarantee a perfect win every time. There will always be a margin of error, a boundary that cannot be crossed without communication. However, if quantum entanglement is introduced into the mix, a phenomenon where two particles become so deeply linked that the state of one instantly influences the other no matter how far apart they are, that boundary collapses. Suddenly it feels as if the players are reading each other's minds, anticipating each other's moves with supernatural precision. What once was impossible under classical rules becomes routine under quantum rules. This eerie connection is what physicists call quantum pseudo-telepathy. To put this idea to the test, researchers turned to the Quantinuum system model H1, an advanced quantum computer that manipulates ions using finely tuned lasers. These ions act as qubits, the quantum version of classical bits. But unlike classical bits, which are either 0 or 1, qubits can exist in a superposition of both states at once. It's like playing chess with pieces that are simultaneously occupying every square they could legally move to. With this incredible capability, the quantum system was set up to tackle the grid game, and the results were nothing short of staggering. Even under noisy real-world conditions, conditions that would normally wreak havoc on delicate quantum states, the quantum system managed to achieve a winning rate exceeding 95%. To put that into perspective, classical systems, no matter how optimized, couldn't come close to matching that level of success. Co-author Rahul Nanjashore described this not as a mere party trick, but as solid, tangible evidence that quantum devices can already outperform the best classical strategies available today. This is a tectonic shift. It signals that quantum computers are not just theoretical constructs anymore. They are practical machines capable of doing what no classical computer can. But the real magic wasn't just in the win rate, it was in the system's design, particularly how it leveraged something known as topological entanglement. Instead of linking a few qubits in a simple, fragile manner, the researchers wove them together into a resilient, interlocking structure, a sort of quantum tapestry. Imagine a fabric made of tiny knots, so intricately woven that even if one part is tugged or disturbed, the overall pattern remains intact. This is what the researchers achieved on a quantum level. They created a topological phase of matter, where the stability and coherence of quantum states were built into the very structure itself. Ordinarily, quantum states are incredibly fragile. The slightest disturbance, a hint of heat, a stray photon of light, can cause them to collapse and lose their quantum properties. But the H1 system was different. Even with only 20 qubits, the way they were connected, the quality of their interaction, allowed them to stay coherent and operational in conditions that would destroy ordinary quantum setups. In the world of quantum computing, quality beats quantity every time. It's not just about stacking up more and more qubits. It's about making sure they work together in a way that's resilient and reliable. And that's exactly what the team achieved here. The implications of this breakthrough are enormous. What happened in that lab wasn't just about winning a clever logic game. It was a clear demonstration that quantum systems are ready to tackle real-world problems. Today's quantum computers can explore countless possibilities simultaneously, making them ideal for solving the kinds of problems that classical computers struggle with. From discovering new life-saving drugs to optimizing the global logistics that keep our economies running, from predicting chaotic weather systems to modeling the incredibly complex interactions within financial markets. Classical computers attack these problems one possibility at a time. Quantum computers attack all possibilities at once. The difference isn't just speed, it's a whole new way of processing reality. However, quantum computing has long faced a massive hurdle: scalability. As you add more qubits to a quantum system, the more fragile and unstable it becomes. This is why early quantum computers, though promising, couldn't scale up without falling apart. But this experiment changes the game. By using a robust topological structure, essentially weaving the qubits into a self-supporting network, the researchers created a system that could handle disruptions without losing coherence. They showed that it's possible to build quantum machines that don't collapse under their own complexity, but instead grow stronger. What's even more exciting is that this achievement is not isolated. It fits into a broader global trend where quantum computing is moving from theoretical to practical. In 2019, Google's Sycamore processor stunned the world by completing a calculation in just 200 seconds. A calculation that would take the fastest supercomputers on Earth over 10,000 years to finish. That moment marked the first serious, credible claim of quantum supremacy, where a quantum machine outperforms any classical machine. China's Zhejiang quantum system demonstrated a different route by using photons, particles of light, to solve the incredibly complex problem of boson sampling, opening an entirely new path for quantum information processing. And in 2024, IBM's Eagle processor shattered previous records by not only exceeding 100 qubits, but maintaining the stability and interconnectivity necessary for real computational work, rather than just experimental validation. Together, these developments are weaving a new reality. Quantum computing isn't a far-off dream anymore. It's happening now, faster and more powerfully than most people realize. And it's not limited to one company, one country, or one architecture. It's a worldwide movement, a technological revolution, with players across the globe racing toward the same inevitable goal: to unlock the next generation of computational power. Of course, major challenges still lie ahead. We need better qubit designs, smarter error correction, and seamless integration with classical systems. But the fundamental truth is that the foundations of the quantum future have already been laid. And experiments like this one, demonstrating quantum pseudo-telepathy at a scale and reliability that was once thought impossible, are the building blocks upon which that future will rise. When we talk about quantum pseudo-telepathy becoming a real, demonstrated phenomenon, it's important to grasp just how much this changes the landscape. It's not just about beating a classical strategy at a clever game. It's about pulling a piece of the future into the present. For decades, quantum computing has lived in the realm of theory, simulations, and tiny delicate experiments that could only survive in controlled lab conditions. But this experiment, showing quantum systems achieving pseudo-telepathy at over a 95% success rate, even with noise and imperfections in the environment, proves something that many doubters thought was still years, even decades, away. Quantum coherence can be sustained long enough and strongly enough to achieve real-world advantages, and not just theoretically, physically, practically, today. To really appreciate the magnitude of this achievement, we have to go deeper into the concept of entanglement itself. Entanglement is the backbone of quantum magic. It's this bizarre connection between particles, where changing one instantly affects the other, regardless of the distance between them. Einstein famously referred to it as spooky action at a distance, because it seemed to defy the very foundations of classical physics. Yet experiment after experiment confirmed it was real. Now, entanglement isn't just something we confirm in physics labs. It's becoming a working tool in the hands of engineers and scientists designing next-generation technology. That shift, from observing to using entanglement, is the critical leap we are witnessing now. In the quantum pseudo-telepathy experiment, the researchers didn't just entangle two particles. They created a network of 20 qubits, all intricately woven together in a topological design. That structure is important because in traditional quantum systems, the more you scale up, the more fragile the system becomes. Noise creeps in from the environment, thermal fluctuations, random photons, cosmic rays. Even the mere act of observing a quantum system can cause decoherence, the collapse of the delicate quantum state into boring classical certainty. But by using a topological approach, creating a self-reinforcing structure, the researchers made the system highly resistant to these disturbances. Imagine a spiderweb stretched between trees in a forest. If you flick one strand, the tension redistributes across the entire web. The web doesn't collapse. It flexes and absorbs the disturbance. The quantum network built in this experiment behaves similarly. A bit of noise or error doesn't bring the system crashing down. Instead, the quantum information remains protected within the structure. This approach is part of what's known as topological quantum computing, an area that many believe holds the key to building large, reliable quantum computers. And the beauty is, it's not limited to this one setup. What they've shown is a proof of principle, a scalable model. If you can create and maintain this kind of entanglement at 20 qubits, there's no fundamental reason you can't extend it to 50, 100, 1,000 qubits, as long as you preserve the topology. That's the road to building quantum computers that are not just powerful but stable. Machines that can run complex algorithms for hours, days, even years without error, tackling problems that are utterly beyond the reach of classical computation. And speaking of problems, classical computers can't touch. This brings us to another crucial point. Quantum computing isn't just about doing what classical machines already do, faster. It's about opening up entirely new kinds of computation. Problems that would take classical supercomputers longer than the age of the universe to solve can be tackled by quantum systems in hours or minutes. Think about simulating the behavior of complex molecules for drug development. Today's classical computers can model simple molecules fairly well, but as the complexity grows, the problem quickly becomes impossible. The number of interactions explodes exponentially, and even the fastest supercomputers drown under the complexity. Quantum computers, on the other hand, are naturally suited to this kind of problem. Because they themselves operate using the same quantum mechanical principles that govern molecules, they can model them directly, efficiently, and accurately. Imagine a future where quantum computers routinely simulate potential drugs, cutting the development time for new medicines from decades to months, or optimizing the logistics networks that move goods around the world, saving trillions of dollars in wasted fuel, time, and resources, or modeling financial systems to predict crashes and manage risk with a precision that seems almost clairvoyant. These are not science fiction scenarios anymore. They are on the horizon, and experiments like this one are laying the foundation for them. But we have to be clear. While the possibilities are vast, the challenges are still immense. Scaling up quantum systems without introducing crippling amounts of error is one of the hardest problems in modern engineering. Error correction in quantum computing is vastly more complex than in classical computing. You can't simply copy quantum information because of the no-cloning theorem. Instead, you have to build elaborate systems that can detect and correct errors without destroying the quantum state in the process. Topological quantum computing offers one promising path by making quantum information inherently resistant to error. But it's not the only approach. Researchers around the world are exploring different architectures, superconducting qubits, trapped ions, photonic systems, topological qubits, all racing to find the best combination of stability, scalability, and practical usability. What's exciting is that we're not seeing one clear winner emerge. Instead, multiple approaches are advancing in parallel. Google's superconducting qubits, China's photonic systems, IBM's heavy hex lattice designs, Quantinuum's trapped ion systems. Each offers unique advantages and faces unique challenges. This diversity is healthy. It means that quantum computing is not a fragile field hanging on the success of a single technology. It's a robust, growing ecosystem where breakthroughs in one area can accelerate progress across the board. And the pace of those breakthroughs is accelerating. 5 years ago, just demonstrating a stable entangled system of 5 qubits was a major headline. Today, 20 qubits acting together coherently, resisting noise, and achieving quantum pseudo-telepathy is a working experiment. Tomorrow it might be 50, then 100, then 1,000. Progress in quantum computing doesn't scale linearly. It's exponential. And as with all exponential technologies, once the curve starts to steepen, change happens incredibly fast. We are standing at the threshold of that inflection point right now, the moment where quantum computers move from delicate lab experiments to robust, world-changing tools. This isn't some distant future anymore. The pseudo-telepathy experiment proves it. We are already beginning to harness quantum entanglement, not just to observe strange physics, but to achieve practical, real-world outcomes that no classical system can match. And as quantum systems continue to grow in power, capability, and stability, the line between what we consider possible and impossible will blur even further. Quantum computing doesn't just speed up calculations. It changes what can be calculated at all. It lets us step outside the box of classical thinking, explore solutions that are invisible to traditional logic, and solve problems that once seemed permanently unsolvable. This is the real revolution underway. Quantum pseudo-telepathy is just the beginning. What comes next? Quantum chemistry, quantum finance, quantum logistics, quantum AI will redefine entire industries and reshape the technological foundation of our civilization. It's no longer a question of if, it's only a question of how fast. If you really step back and look at the big picture, what's happening with quantum pseudo-telepathy is a signal flare for a much larger revolution that's just beginning to unfold. It's a moment in history when an entirely new kind of information processing is moving out of theory and into the real world. What was once the dream of a few visionary physicists, that quantum mechanics could be harnessed for computation, is now being realized by engineers, scientists, and technologists across the globe. And the key proof is experiments like this one. Not just a clever game, not just a flashy demo, but a robust, repeatable demonstration that quantum advantage is real, achievable, and scalable. The idea that two players can seem to read each other's minds, winning a logic game with a success rate that classical physics says should be impossible, isn't just a neat trick. It's the living proof that entanglement can be engineered, controlled, and used as a practical resource. When the researchers at the University of Colorado Boulder and Quantinuum set up this experiment, they weren't just trying to beat classical strategies. They were testing the very boundaries of what information means. In the classical world, information is local. It moves from point A to point B. It follows paths and wires. But in the quantum world, information can be non-local. It can be spread across multiple locations, linked by entanglement in ways that no classical system can replicate. That's why even the most advanced classical supercomputers can't match what a relatively small quantum computer can achieve with the right structure and entanglement. It's like trying to send messages across the ocean using smoke signals while your competitor is using fiber optics. The medium itself is fundamentally different and vastly more powerful. And that's why quantum pseudo-telepathy is not just a curiosity, but a demonstration of quantum superiority in action. Of course, we're still at the early stages. Today's quantum systems are still small compared to the classical giants that run our world. The Quantinuum system used in this experiment had 20 qubits arranged in a careful, structured network. By contrast, a modern classical processor might have billions of transistors, but raw numbers don't tell the full story. In quantum computing, it's not just about how many qubits you have, it's about how well they're connected, how stable they are, how coherently they can act together without collapsing into classical noise. It's about how well they're connected, how stable they are, how coherently they can act together without collapsing into classical noise. Quality over quantity. And that's what experiments like this one highlight so clearly. The topological approach they used, weaving the qubits together like a complex tapestry, is crucial because it's resilient. It doesn't matter if one thread gets tugged a little, the overall pattern holds. In practical terms, that means that quantum devices based on this principle can survive the messy, noisy, unpredictable conditions of the real world. They don't have to live in perfect isolation inside pristine labs. They can function, thrive, and scale in the same chaotic environment where real-world problems exist. And scaling is the name of the game now. If we can scale these systems up to hundreds or thousands of qubits while maintaining topological protection, the kinds of problems we can solve will explode in both number and complexity. Quantum chemistry, materials science, artificial intelligence, logistics, national security, climate modeling, all of these fields are standing on the brink of transformation. It's not that quantum computers will replace classical computers entirely, it's that they will complement them, taking on the hardest problems that classical machines simply can't crack. Already, companies and governments are racing to prepare for this future. Major tech firms like IBM, Google, Microsoft, and startups like Quantinuum and Rigetti are pouring billions into quantum research. National governments are investing heavily too, seeing quantum technology as a strategic priority on par with nuclear energy or the space race. Why? Because the first organizations to harness real, scalable quantum power will have an enormous advantage, economically, militarily, scientifically. And the most fascinating part is that we're not just talking about faster computing. We're talking about fundamentally different capabilities. Quantum computers can explore solution spaces that are literally unreachable by classical means. Problems that are practically infinite in their complexity suddenly become approachable. Optimizing global transportation networks with millions of variables, discovering new materials with tailored properties for everything from energy storage to aerospace, designing drugs and therapies targeted at specific proteins or genetic markers, simulating nuclear reactions with pinpoint precision. Each of these achievements could have a world-altering impact. Solve logistics optimization, and you slash global carbon emissions by huge percentages. Solve material discovery, and you create lighter, stronger, more efficient components for everything from cars to smartphones to rockets. Solve drug discovery, and you open the door to cures for diseases that have eluded us for centuries. The potential isn't just enormous, it's transformational. But with great power comes great responsibility. Quantum technology also raises serious ethical, economic, and security questions. If quantum computers can break the cryptographic codes that secure today's internet, how do we protect sensitive data? If only a few nations or corporations control quantum computing, what happens to global equity and power dynamics? These are questions that society will need to confront, and soon, because the timeline is not decades away anymore. It's years, maybe even less. The quantum pseudo-telepathy experiment is a bright signal flare that we're entering this new era. It's proof that real-world, scalable quantum systems are not just science fiction, but emerging science fact. And it's a call to action for scientists, engineers, policymakers, and everyday people to start thinking about how we build this quantum future in a way that's responsible, equitable, and beneficial for all. There's something deeply poetic about how this all circles back to the very heart of quantum mechanics, the interconnectedness of things. In classical physics, the world is made of separate parts. In quantum physics, those parts can be entangled, bound together in ways that defy intuition. And now, through careful engineering, that same entanglement is becoming the foundation of a new kind of machine, a new kind of problem solving, a new kind of human achievement. Quantum pseudo-telepathy isn't just a cool trick. It's a glimpse into what happens when we stop fighting the weirdness of quantum mechanics and start using it. When we embrace the strangeness, the possibilities multiply. Entire new industries, sciences, and technologies will emerge from this foundation. And the boundaries of what we consider possible, the walls classical physics built around our imagination, will come crashing down. The journey ahead will be challenging. It will require breakthroughs in materials science, in error correction, in quantum software, in system architecture. But for the first time, we're not walking in the dark.